Okay, so I think we can start now. The first thing is that the course is going to be in English. I hope that's okay with everyone. Something I forgot to bring today is the syllabus, but I think you may have it already, right? So just to make sure, this is a course on F-singularities. So it's going to be hybrid, so there will be people here attending in person, and at least so far there are 6 people online. And so the good thing is that we're going to be able to record a lecture, so if you miss one, you can just go and look at them. I don't know exactly how it's going to work, but I understand I'm going to be sent a link where those lectures can be downloaded. But I think it may be that I'm going to have them on my website or something like this. But I'll let you know by email later on. Actually, talking about it, please send me an email. So if you want to be in the email list, maybe the people who are like official in the course don't need to do this because I already have their emails. So, but if some of the people that are just attending for fun wants to be, like informed about class cancellations or like the updates for the notes or the recordings of the lectures, please send me an email so that I know that you exist and you want to be informed. Okay? Or maybe I can give you my email. I'll see Matt. What else? So they will be office hours. So which I hope you want to attend from time to time. So if you want to go to my office, go on Tuesdays from 2 p.m. to 3 p.m. Okay, so if you want to, this is office. If you want to go on Zoom, you can do it on Thursdays, same from 2 p.m. to 3 p.m. Or just by appointment, okay? If this time doesn't work for you, like just send me an email and we can set up a different time, either in person or on Zoom. So another detail about the book, about the course is the book. There is no book. However, there are some surveys and some papers and things like this that we're gonna follow, but it's a whole mess, right? So what I want to do is to write some notes, which are going to be at first very rough, but will contain all the material I'm going to be presenting, the most important proofs, and most importantly, a whole bunch of exercises that I hope you can try. So, right, like it's very difficult to learn the material just by listening to it. So if you really, really want to learn it, I recommend you to go through the exercises, which are essentially optional, right? So yeah, I'm gonna be writing notes and I'm going to be sending them to you on a weekly maybe, or perhaps even better, I'm just gonna post them on my website and you can just download them when you need them, okay? So I guess the last detail about the course are grades. So book, I will be writing notes. So grades. So first things that are very flexible. I can say this, but these are extra flexible if you're a PhD student. So, but what we're gonna do is that, so at the end of the semester, I'm gonna ask you for some of the homework problems. I say that on the notes, there will be a whole bunch of exercises. And at the end of the course, with 3 weeks in advance or something like this, I'm gonna ask you to submit at most 3 problems, okay? And it would be cool if also towards the end you could present a lecture. You know, I'm gonna tell you, why don't you present a proof of this result? You come here and you present it. I'm gonna give you the material and everything you need to do the presentation. But honestly, if you don't like this, you can let me know and we can arrange something else too. Okay. So, yes, I think that's it for the organization of the course. So, yeah, so the other thing is that I don't quite know what to teach because I don't know who is going to be attending. And specifically, I don't know how much commutative algebra you know. So for that reason, I really would like if you can tell me if the course is too difficult, if I'm assuming too much, or too little perhaps, so that I can adjust better. My idea is to tailor the course as much as possible to your needs. Okay? So please don't be shy and tell me like if you need, if I'm doing something wrong, okay? If I'm assuming too much or whatever. So in particular, it was very challenging for me to prepare this first lecture because again, I really don't know how much to expect from you. So, but I think what we're gonna do is, okay, we're gonna study the theory of F-singularities, but this one could be a little bit advanced in terms that I may need a lot of commutative algebra. So when that's the case, for example, I won't assume that you know what a Macaulay ring is. Or I won't assume you know much about local homology. Okay, so when these things happen, we're gonna have a real quick crash course on that. And then like we're gonna do the F-singularity part. But it's gonna be a balance, right? Like I'm gonna maybe assume that you took a first course in commutative algebra so that you know about modules of the rings, localizations, primary decomposition, interior rings, integral extensions. I don't know what else is there, maybe completions. That's more or less the first course in commutative algebra. But a second course would be about local homology, Cohen-Macaulay rings, Goranson rings, Kotsur complexes, I don't know what. Maybe regular rings too would be there. And that we're gonna do it like a little bit over here. Because actually I don't think that at the CMAT you necessarily covered that previously, right? I'm not sure. Yes. Yeah, so but it's gonna be a crash course anyways, and on that type of things. So for example, today we're gonna be talking about regular rings, which I don't know if we have covered before, but it's like, I don't know. So today, for example, it's going to be a crash course on regular rings. So, and I'm gonna use actually today's lecture to test a little bit how much I can assume you know about commutative algebra. So I don't know, is there any question? Maybe on Zoom? If you want to participate on Zoom, just unmute yourself and you can just say whatever you want to say. I don't know what's Zoom. Any questions though? Nothing? So then we can start. So I was said this is the first on F-singularities. Hold on again. In particular, it is a course on singularities. Okay, and to know what a singularity is, we have to know what regular rings are. So the first section will be about regularity. Okay, which is by definition, or I guess singularity is the lag. So let me say, so singularities are the lag of regularity. Regularity. So what are regular rings? So to know what a regular ring is, so that's a tricky question. So it turns out that, I don't really want to say this, but the right way to think about regularity is through it's called homological characterization. So we're going to do that first. I think you may have seen before regular rings in your commutative algebra course, but I think it's very unlikely you saw the homological characterization in terms of projected dimensions. And so somehow, one could make an argument that's the best definition. And so perhaps next week we're going to try to prove Kunz's theorem, and the proof goes through this characterization. So we're going to see that first. So let's talk about projective resolutions. So what is this? So for this, we're going to fix R a ring. And let's take N to be an R module. And so you want to understand N, right? So what you do? Something you can do is to cook up a set of generators. Right? And so cooking up a set of generators of your module, you know that you can think about it as a surjection from a free module. And what is the basis for that module? That set of generators. Okay? And this is much easier to understand, right? So this is, so you would wish that every module, was free, but it's not. So, but at least you can find a surjection. And so this map is going to have a kernel. Let's call it K1. Right? So it's going to have a kernel, but that kernel may not be free. Right? So if these are the generators, right, of your module, the kernel represents the relations between those generators and therefore the lag, or how far away N is from being free. Okay, but then we can repeat the process, right? Then we can cook up another free module representing the generators of K1. So here we have generators for the module, and here we have generators for the relations. And so this map here is going to have another kernel, which represents the relations between the relations. Right? And so what you do is that you repeat this process. And so you end up with an exact sequence of free modules. So the idea is that, okay, modules are not necessarily free, but at least they can be represented by a non-exact sequence of free modules, right? And so this is a so-called free resolution of M. And perhaps we're going to talk about it at some point. It's only to decide if that's a good idea or not. But you know, in the modern perspective of the right categories and so on, this is the right way to think about that through a resolution like that. So a bit of terminology. This Ki are referred to as the CCG module. How do you spell this? ZCG module of the free resolution. So we're going to use the following notation. We're going to use P bullet to represent the free resolution. Okay. And so you may be wondering why I am using the letter P here and not F. Well, the first reason is because F is reserved for Frobenius, but also because free modules are projective. So remember, free implies projective. I guess a good definition for projective. So a projective module is a module P, right? So that, or such that, whenever we have a surjection onto that module, what happens? The sequence splits. So that's what projective means, if you want an extra definition. And an example are free module. So, however, the converse is true in a very specific case, which is if the ring is local. So you can think of projective as locally free. So this is if R is local. If the module is finally generated, that's relatively straightforward. You can use Nakayama's lemma to see that, for example. But in general, talking about absolutely general modules is a theorem of Kaplansky. A bit harder, but it's true. So, and so it turns out that it's better to work with projective resolutions in general. They're more stable than check operations. Actually, you would see a very concrete exercise where you can see why one uses projective resolutions instead of free ones to write down the theory. Even if in practice, you can always hook up a free resolution. When you start doing operation on them, you often need the projective ones, okay? There will be an exercise in which you can see that. And so this is, yeah. So free resolutions are projective resolutions. And a projective resolution is just the same thing with projective instead of free, okay? So actually, we just proved that the category of R modules have enough projectives, meaning given a module, you can hook up such a non-exact sequence that surjects onto N. Okay. So that's the terminology people use. Now, here's the key concept: projective dimension. This is how complex the module is. Projective dimension. So let's define it like this. We're going to take a module, and we're going to define its projective dimension as follows. I guess we should write it maybe something like this. But if the ring is clear, then we just write this. And so what this is the following. So, but it's going to be a minimum. Okay. Of the following set. So, well, I'm installing a set right down like this because the set I'm going to write down will be empty, and so it may not have a minimum. In that case, you set the projected dimension is infinite. But let me just write it down like this. So what we're going to do is that we're going to be looking at the length of projected resolutions. So you're going to look at the ends such that there exists a projected resolution that stops after n. So such that pi is 0 for all I bigger than n. So technically speaking, to extract the minimum of a set of integers or positive integers, I need that set to be non-empty, right? So if it is non-empty, it means that there exists a projective resolution of finite line, a resolution that stops at some point, right? And when you start doing this, a CCG module vanishes. Okay? In principle, this could go forever, but if it stops, then this happens, right? And so you can extract the minimum n with that property, the minimum length of a projected resolution. So I don't know if it makes sense, but then if this set is empty, we're going to agree that its minimum is infinity. So let me just write down this. Minimum of the empty set is infinity. In other words, like if we can never stop the process, then we say that the module has infinite projective dimension. It is extremely complex, right? Because when you start writing down the CCGs, you can never, stop finding relation between them. Because this is the relations of the relations of the relations of the relation never stop. Okay, so it's a very complex module. Okay, is this definition clear? So if you have an exercise and is projective, you can only give the projected dimension of n is 0. Okay, by that, just to make sure you understand these things very well. And actually, I'm gonna write down a lemma that illustrates why this notion of projected dimension is only well behaved if one works with projective modules and not just free ones. So here is a lemma. And so this lemma 1.3 in the notes. It says the following: suppose that you have two CCGs of the same length. So we have one like this and another one with primes. So, and when I write P, I mean that P is projective. I hope that's clear. What could be a good color? Maybe blue? Is blue a good color? Maybe red. Let's see this thing. So this is our projective. Okay, and so these are the assistants. So here's the lemma. And this lemma will have a whole bunch of important consequences. So then, and this, you will see why this is a lemma, because the first statement is kind of weird. But I guess you have to think about it. So what I'm going to do is that I want to take Kn, and I'm going to take the direct sum of Kn with this one. P prime n minus 1. But then I'm going to go up and use Pn minus 2, and so on. Okay? And over here, I'm going to have this one, Kn prime, direct sum. Now I'm going to go up. Pn minus 1. Then I'm going to go down. So on. The first part of the lemma states that these two direct sums are isomorphic. So it's sort of trying to tell you like both resolutions contain more or less the same information. Okay. However, this has a very important consequence, which is far from trivial, which is that Kn is projective if and only if Kn prime is projective. Remember that a characterization of projectivity is by, what can you say, a module is projective if and only if it is a direct summand of a free module. Right? Using that characterization, you will see that one is projective if and only if the other one is. Right? This is the really important part of the lemma. This part here. But it follows from A. A is the hard part. Okay? So, and what I wanted to mention is that this is not true if you work with free modules, right? This is not true for free. Like, if you replace projective for free, is projective the property that is stable here? Okay? And so it is because of B that we work with projective modules, essentially, instead of free resolutions. And so A is going to be an exercise. It is just annoying, but it's not too hard. So in the notes, they give you the outline of how this goes. Essentially, it is induction on N. And the case N equals 1 is the key one. So I'm going to let you do the case N equals 1. That's very tractable, and you do it. And then for the inductive step, what you do is that you argue that you can reduce the case N equals 1. And then it is done. Okay? But again, like the only way to learn this material is to do the details, okay? To work them out. So this proof is going to be an exercise. But what I care about is B, because B has a whole bunch of consequences. So, well, there are a whole bunch of consequences, but then let me illustrate the most important one. So, how are we doing with the time? Okay, let me just give you one corollary. Which are all exercises. But they're easy. They really follow from B. You just think about B and what the exercise says, and then you have that. Okay, let me give you a whole bunch of properties. First of all, thanks to this, you can prove that the projected dimension of n is less than n using this notation here, if and only if. What do you think? Kn is? Projective. Which is not obvious, right? Like, it's not obvious that if you have a projective module here, that you can say that the projected dimension is n, because you don't know if there can be a shorter one. Oh, sorry. Well, yeah. Well, that the projected dimension is less than n. It's not trivial. Unless you know that Kn is projective. Pardon?
Excuse me?
See? Yes?
Yeah, could you move the camera?
Oh, sorry. Oh, yeah, sorry about that. Battery supply. Okay, sorry. This is another property that will be important later on. Again, these are all exercises, but these two are actually used for the following one. This is really important. This one, you have to make sure you do it. And it is that the projected dimension can be computed by localizing. It's going to be the supremum of the projected dimensions of all the localizations of prime ideals. That's a key property. So you look at the projected dimension of all the local rings, and then the maximum one is the projected dimension of n. This is the key step. That projected dimension can be studied locally. Okay, so actually these sort of ideas were introduced to prove that regularity is well behaved, you know, when you localize, which is far from trivial. But then it is the characterization of regularity through this sort of invariants that let you do that, because they have this property. So this is the key property of projected dimensions. And of course, you can also put here the maximum spectrum. You can reduce the case of maximum ideas. So in principle, this one is going to follow from these two. So I'll let you do that. Another one that follows here is that the projected dimension of the direct sum is the maximum of the projected dimensions of the two sums. It's not too hard. There is another property. Which is actually the behavior of projected dimensions in exact sequences. This is going to be an exercise. is hard, but it's true. If you have an exact sequence, the way this goes is that you want to compute like a projected resolution for this, another one for this, and you want to look up one for the middle. And then you compare like how far you can go and so on. But so the point is like the projected dimension of n is bounded by the maximum of the projected dimensions of n prime and the projected dimension of n2, n double prime. Well, I guess there's a first part here. If two of them have finite projected dimension, then so does the third one. And in that case, you can compare them like this. If the inequality is strict, this is a very important trick that is going to come up later. Then the projected dimension of the co-kernel is equal to the projected dimension of the kernel plus 1. So again, this is a wonderful exercise to make sure you understand projected dimensions. If you really want to understand them, I'll let you try it. It's a bit difficult in the sense that you have to do a whole bunch of homological algebra, which I don't know how comfortable you are with it. But if you get stuck, you can ask me, we can go through it together. Okay. So of course, it's very useful to know how projected dimensions behave on short exact sequences. Better, we have to move it. I can do it too. I don't think it's so difficult for me to do it. Okay. It's a very important environment for a module. Now let's talk about minimal free resolutions. Right, because a free resolution is far from unique. And you want to look up one that is as simple as possible. And so in the local case, we can do the following. So definition, let's take R, comma, N, comma, K to be a local ring. I think this is the first time we encounter this notation, but it's going to mean the following. This is the maximal ideal. And this is the residue field. Okay. And I guess local always means Noetherian, okay? By definition, well, local means that there is only one maximal ideal. But also means Noetherian. In particular, the maximal ideal is finally generated. So this is the setup. The other ingredient is that we're going to take M, a finally generated R module. And I don't remember what to do again. Oh, very good. Thanks. And so the third ingredient for the definition is a projective resolution of M. So it's minimal if, okay, let's write it down. So we have this projective resolution, right? We started choosing generators, right? But we want to choose those generators minimally, right? And so Nakayama's lemma let us do that, right? Like we can tensor this module by K, we get a finite dimensional vector space, we choose a basis there, and we limit it to a minimal set of generators. And so we're going to choose P0 in that way. And we repeat like that. So every time we choose generators for the CCG, we choose it minimally. So if we have maps here, what is a good name for these maps? Phi, I guess. So this is going to be Phi0, Phi1. So the index matches the target. Okay, so it's minimal if the condition I just said can be expressed like this. The image of Phi lives inside and Pi. Or more concretely, right? Like, since N is finally generated, these modules can be chosen to be of finite rank. And therefore, these Phs are nothing but matrices, right? So what we are claiming is that the entries of those matrices live in M. i.e., Pi is a matrix, with entries in M. I think that was an exercise, but it's just about thinking the definition in different ways. But in practice, that means that when you choose generators of the CCGs to construct a sequence, you choose the generators minimally. These guys are cool because it's going to let us define the Betty numbers of a module. Let's see how much I want to say here. So a remark. So this is what I was saying, like if you have a minimal resolution, if this is minimal, so well, some notation that we're going to be using all the time. It's a notation to represent the minimum number of generators of finally generated module over a local ring. So in the setup of the definition, the minimum number of generators is by definition, or well, by Nakayama's lemma happens to be the dimension of M modulo M. This is a K vector space, right? Because this module here is none other than K, the best change of M to the diversity field, right? It is a finite dimensional vector space. It has a dimension, and by Nakayama's lemma, that dimension happens to be the minimal number of generators of M. Okay? So we're going to use this notation. And when you have a minimal resolution, you have the following properties. This is the whole point of a minimal resolution. First of all, P0 is going to be a free module of rank, right? In this case, this is going to represent the rank of that free module of rank equals to the minimal number of generators of n. That's what I was saying, right? Like when you write down P0, you choose generators for n, but you choose them minimally. And more importantly, so the minimal number of generators of the I CCG, remember the I CCG is the kernel. I need to get the numbers right here of phi I minus 1. The minimal number of generators of the I CCG equals the rank of the I free module in the resolution. That's what I was saying, right? Like when you choose PI, you take a minimal set of generators for KI. In other words, a basis for KI modulo n. Okay? These are the key properties to have in mind. And I think this is just an exercise for you to think about. Again, you really have to do the exercises. It's now or never. Minimal free resolutions always exist. That's an exercise too, Nakayama's lemma. Here is another exercise, which is a consequence of the lemma I was telling you about, the first lemma we wrote. It's a very important exercise. Suppose that you have two minimal free resolutions, as before. You have P and you have P prime. Minimal free resolution. You have two of them. Some chalk. Then, again, a minimal free resolution is not unique, right? It's not that the modules are not unique. But what is unique about them? The ranks of the free modules. And so it's almost unique. And so this is the consequence of this exercise. The rank of Pi is equal to the rank of Pi prime. And so the following definition makes sense. This is the definition of Betti numbers. So, well, to define them, we need a local ring, we need a module that is finally generated. And so we can define the I Betti number of n, I Betti number, and it's going to be mu Pi. And what you do, you take any minimal free resolution. And because of this definition makes sense, where you take a minimal okay? So you see that the Betti number is the dimension of the space of relations, right? What is the minimal set of generators for the CCG of a minimal free resolution? Right, so this numbers really tells you how complex your module is. But to be defined, you need the local base. So, as a remark, sometimes you will hear people talking about the Betti numbers of the ring R, but the Betti number of the ring are absolutely trivial, right? They're all zero, but the first one, because R is a free module. But what people refer to are the Betti numbers of the residue field. Okay? And those are very, very important for singularity theory. No, but yeah. So here are more. So again, today we're just having a crash course on this sort of stuff. So that's why most things are exercise. As soon as we get to F-singularities, we're going to prove more things in class. But again, I really don't know how much you already know of this stuff. Is it more or less new to you? Okay. So another exercise. So what do you think is the projected dimension of a module in the local case? It's going to be the largest I, such that the Betti number is different from 0. If the Betti numbers are never 0, then the module has infinite projected dimension. Here is a very cool exercise. I was thinking to do this here, but I don't think we're going very fast. So let me give it as an exercise. This shows you why these minimal resolutions are very important. Actually, this also proves why the Betti numbers are independent of the resolution. They can be computed directly as follows. The Betti number of a module, let's see. Well, let's think about the 0th Betti number. The 0th Betti number is the minimal number of generators of n, right? So, in particular, I told you is the dimension of k tensor n. You do a base change, you get a vector space of finite dimension, and that has a dimension. So, what do you think is going to be the I Betti number? Is going to be the dimension well, k tensor n is just another way to think about the 0 Tor functor. When you do this, right, it goes like this. The order doesn't matter here, it's going to be right. So it is the I Tor functor, so I Tor functor of k with n, which is a k vector space. Right, because how you compute this Tor? You take a projective resolution of n, right? You tensor with k, and by tensoring with k, that exact sequence becomes a sequence of vector spaces. And its cohomology is going to be a vector space, which is this. This is why it has a vector space. Why this has a k structure on it, right? So let's do this exercise. It's very fun. But if you get stuck, let me know and I can help you out. And this has a very, very cool consequence. Look at this. So suppose that you want to understand the projected dimension of a module, right? So this tells you that what you have to do is to look at this Tor modules, right? And you want to look at the maximal I such that they are non-zero, right? So the 0th one is 0 if and only n is 0, but I can down. So you try to see when this stops being non-zero, right? If ever. But this is the cool thing, right, about Tor. Tor is symmetric, right? Remember, to compute Tor, you compute a resolution of M. However, you could also compute it by a resolution of K. And that has the following consequence. That this is less than the projected dimension of K as an R module. Look at the beauty of this theorem, right? It tells you that the most complex R module, as far as resolutions go, is the residue field. If you know this is finite, you will know this is finite. So, again, this is an exercise. Again, I don't want to do the details here because otherwise we will never ever talk about F-singularities. So that's cool and everything. Where we? Okay, finally, we can talk about global dimension of a ring. Global dimension. I didn't choose the notation here in the note. Okay, so if you have any ring whatsoever, we're going to define this global dimension. Any ring is going to be a supremum that for most rings is going to be an infinite number, but okay. So you take the supremum of all possible projected dimensions of finally generated modules. Okay. By definition. Of course, this could be infinite. This is only finite if every module has a finite projected resolution. Okay, so let me give you an example. We're going to be on proof probably on Thursday. You remember Hilbert's CCG theorem, right? Hilbert's CCG theorem says that the global dimension of the polynomial ring is finite, but moreover is bounded by the dimension, which is n in this case. So there are rings with finite global dimension, but very little. Actually, we'll see that very little rings have finite global dimension. They would be the regular ones. That's the punchline of this week. Did you guys see the Hilbert CCG theorem at some point? Or this is new to you? If you didn't see it, reach out to your algebra prof and complain about it because it's a must. Okay. But we're going to give a proof here. It's not super hard to prove. It's about the two complexes and all that. But we're going to give a proof here. The reason for this is the polynomial ring is regular. That's the punchline. So, but corollary. Let me do it like this: like the global dimension of a local ring is the projected dimension of the residue field, right? Because I erased the definition. This is stupid. By definition, it is the supremum of all these numbers. But actually, in the local case, the supremum happens to be a maximum, right? And you reach a maximum at k. So it's a projected dimension of the residue field as an R module. In fact, more generally, you can say that the global dimension, and this is the beauty of this theory, that the global dimension is well behaved with respect to localization. So, but you can say the global dimension let's just say this, it's going to be the supremum, and you go through the projected dimensions of all the possible residue fields. This is my notation of the residue field of P. When you go through the spectrum of R.
It's for any R.
For any R. In the local case, well, there's only, well, no. You can do it for the maximum ones.
But R is Noetherian in that case?
No.
Even if R is not Noetherian.
Local Noetherian. Yeah, Noetherian. Let me say Noetherian. Yeah, because it has to be local. Okay, so, but the important one is that in the local case, you can do that. The time. Any questions so far? To summarize, what I need you to keep in mind is that you can measure the complexity of a module by its projected dimension, right? It tells you how far away you have to go into a minimal free resolution, right? Well, in general, for a resolution, the minimal ones only exist, let's say, for local rings. And the global dimension of a ring tells you how complex resolutions are in that ring. We know that, for example, for polynomial rings, it's no more than n. And the question is, well, when does this happen? And, well, I give you the punchline, and the punchline is like if the ring is singular, this breaks, this is infinite. So you can always find a module that is arbitrarily complex. You know, a singularity destroys the beauty you see in the Hilbert-Sticky theorem. And that. Okay, now I need to ask a question here. I really don't know how standard this is if you have studied regular sequences and that. I don't know if that's common in computer algebra class here, more or less. So we're gonna have then a little crash course on that. But we're gonna come back to that later when we talk about local homology. For now, I just use the formula here. Okay, so actually here in the notes, I put it as a remark because I really don't know how standard this is. Well, let me do let's talk about regular sequences. And depth. So take a ring and take a module and take an element of that ring, right? These things, so multiplication by R give you an R linear map, right? You take M, right? This is the definition of an R module, right? An R module is an abelian group such that there is a ring homomorphism from R to the automorphisms of, sorry, to the endomorphisms of M. So having this is perfect. So you have an R linear map. So R is regular. This is the definition. Regular on M if this multiplication by R is, well, first injective. In other words, the only thing killed by multiplication by R is 0. Okay? And R is not surjective. Okay. In other words, if R times M is M, you don't want that. This is sometimes a silly condition. Because if R is in the maximal ideal in a local case, this never happens unless M is 0 itself. But for example, 1 is not a regular element. The element 1 is never. And notice that this first part is the definition of a non-zero divisor, right? But the regular element is a non-zero divisor. That's it. Almost. Okay, so. And so then we can talk about the regular sequence. So if you have an R is a regular sequence, on M, people also say an regular sequence, and I may use both, is two things. First of all, the first element in the sequence is a regular on N. And second, Ri is regular on M modulo R1 through Ri minus 1. You take your module and you go out by this submodule, right? And Ri has to be a regular element there. Okay. That's a regular sequence. Okay, so if you have an ideal, then you can define the depth of A on M. Okay, the notation is depth. It's an R module like this. And this is by definition the maximal length of regular sequence. Let's say a regular sequence. Okay, so you're looking for regular sequences, but you're going to look for those whose elements are in A. Whose elements are in A. Okay? Now, this is the lane definition. This is not, but it's the one that it can be, explained that easily. The right definition is with local homology, so we're going to come back to it later. But let me just write this down. Where are my notes? So, this is a very, 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 very important notion. And commutative algebra is all about it. Okay. So, in the local case, right? In the local case, there is a special ideal, which is the maximal ideal. So we write simply the depth of M. Well, I guess if the ring matters, we can write this. But it's simply by definition the depth with respect to the maximal ideal. Which actually you can put here R because regular elements can never be in this. Okay. So, and this is my question here. Fact, it's not very hard, but let me see if you know it. Otherwise, I'm going to maybe break it down for you as an exercise. I really don't know if you know. The depth of M in the local case is the minimum. The depth is dual to the projected dimension. So it's the minimum. What are you going to do? Before, we were talking about the Tor modules, right? For the depth, what you do is you look at X. So you're looking at where is the minimum I such that this is never 0. So actually, let's think a little bit about x0. X0 is home from K to N, and home from K to N is the so-called suffle of M, right? It's going to be the elements of M that are killed by the maximal ideal. So is that never 0? If that's not 0, because M is well behaved, then this minimum cannot be I equals 0. So you have to go to the next level. Okay? So the point is that the higher the depth, the better the module. So we're looking for high depth. For projected dimension, we're looking for low projected dimensions. Okay? But do you know about this fact? Maybe on Zoom, is this something you know about? Or maybe it's better.
Yes, at least myself.
Okay. It's not very hard to prove. Maybe what I can do, because this is something one has to know, like it's good to do as an exercise. I'm going to break it down maybe in a series of steps on the notes so that you can work it out yourself.
Could you repeat the observation you did on the circle? Because that was interesting. What do you mean by that?
The observation about what, sorry?
The socle. You mentioned the socle. Yeah,
Yes,
the
so
X, well, the homomorphisms from K to M. Well,
yeah, so if you put I equals 0, then X 0 is hom. So you will have hom from K to M.
mm-hmm.
But K, so K is a module that is generated by one element. Right?
Yes.
So to define a map, you only have to know where to send one.
Yeah.
And so you have to choose an element here. But for
yeah,
the map
so,
to be well defined,
okay.
it has to be K by M. So this is none other than the elements of M, such that M times the maximum ideal is 0.
Yeah.
That's often referred to the socle of the module.
Okay.
Yeah. Which is going to come back later at some point, most likely.
Great. Thank you.
Okay, so you have the depth of a module that has to do with X. It actually has to do with cohomology, and we'll see that later X is sort of dual to local cohomology in a sense. But this characterization here is very useful because of the following formula, which is referred to. I need to spell this correctly here. Auslander book. It's a very useful formula. In practice, but it's also very satisfying conceptually. So if you have, well, the setup is the setup in which things make sense. So we're going to take a local ring. And we are going to take M. And what we're going to ask about M is that it has finite projective dimension. Okay? Then what I was saying before is true. If the depth is big, projective dimension is low, and vice versa. And actually, they're complementary to each other because they add up to the depth of R. So if you take the projective dimension of M and you add its depth, the answer is always independent on M. It is the depth of R. Well, I don't know how obvious this is, but it's never bigger than the dimension of the ring. Okay. And for example, we'll see later that a ring is Cohen-Macaulay if and only if the depth is equal to the dimension. That's the definition of Cohen-Macaulay ring, if you will. So you see, if this is very little, this is very big, and vice versa. So we have 10 more minutes. In particular, this has a remarkable consequence, which is that the depth of a ring is a bound for its projective dimension if it happens to be, for its global dimension if it happens to be finite. So, in particular, if the global dimension of R is finite, then the global dimension of R is no more than its depth. So either the global dimension of a ring is infinite, or it is no more than its dimension. And actually, we will see that it's going to coincide with its dimension. I guess for finite dimensional rings. Okay, I prepared a proof of this, but I don't think there is much time left. What should we do? The proof is not difficult given this definition. Do we do the proof? Let me see if that's a good place to finish, and if we have the time to make a few remarks. I think the proof for this would be a good place to stop for today. So I'm going to do a particular case of this proof. And we're going to see why this characterization of depth is very useful. Proof. So first case, suppose that the protected dimension of M is 0. What does that mean? M is free. If M is free, then X commutes with direct sums. So it's going to mean that the depth of M is the depth of the ring. The depth of M equals the depth of R because M is a direct sum over some index, whatever. But X here, look, it's going to commute with that. So whether or not that is 0, it's going to depend on the X with R here. So these two depths are the same. Okay? Good. If the projected dimension of M is equal to 1, what does that mean? Let's think about it. It means actually here I need M finally generated 2 for this to hold. So if the projected dimension is 1, it means that you can understand M via a following an exact sequence like this. Right? And what is the wonderful thing about X is that it is like a homology functor. So it's going to be, if you have this, you automatically get an exact sequence. Okay? So it means, so let me take this and let me take it minimal. Minimal free resolution. So technically speaking, N is the 0th Betti number, this is the first Betti number, right? And so when you look at what happens on X, let me call this phi. So I don't want to write down the long exact sequence. This is slightly too annoying. Let me do it. So you have X of K, or direct sum M, X K, R direct sum N, and then here you're going to have X R modulo M, and then X I plus 1 are, what am I doing? It's with K, sorry. This is K, and this would be K. It would be R tensor M. Direct sum M. And so the point is that when you look at here, this is always 0 because the resolution is minimal, right? Because what are you doing here? What you do is that you apply xi to this map. But this is just a matrix, right? So X is going to commute with that matrix. But since this is minimal, those entries belong to M, and therefore are 0 modulo K. And so X is 0. So the key fact here that I'm going to let you think about is that the Xi K of this P, which is a matrix, is 0 because the resolution is minimal. And so by doing that, the whole point is that the non-exact sequence becomes the following. Have this one, and then you go to, I should write down smaller. And then you go to S from K to M, and then you get X to I plus 1 R K R direct sum M. Okay, and so you have this sequence of K vector spaces. And so this is 0, if and only if this is 0. Actually, you can commute here, right? So this is 0, if and only if this is 0, and this is 0. So what happens? The depth of M equals the depth of R minus 1. Yeah. As required. But what you have to appreciate is that the definition of depth in some of these X functors, right? Because that's the interplay between free resolutions and the X. So if the projected dimension is more than 2, you do induction. What does this mean, right? This means that you have your M, you can hook up a free module of rank M, and then there will be a kernel. But what do you know about the projected dimension of M? The projected dimension of M is equal to the projected dimension of M minus 1. So you do induction. But how do you do induction? What functor did you apply here? Apply apply this functor to that exact sequence. And what happens? You get a non-exact sequence with a whole bunch of X, right? And so look at what happens, and you will find that let me get the thing right. So by a similar analysis, you're going to conclude that the projected dimension of M is equal to the projected dimension of M minus 1. And so apply the inductive hypothesis with this, and you are done. But again, you have to appreciate that the depth is given by this X, that there is a cohomological interpretation of depth that lets you have an interplay between resolutions and depth. Okay, so we're going to stop here. This was a crash course on projected dimensions and depth. And next time, we're going to see how we can use this to understand regularity. In particular, the focus of next class will be to prove Serre's theorem that characterizes regular rings in terms of finite global dimension. And one can argue that that's the right way to talk about regularity. Okay. So that's going to be next time. So please remember to send me your emails so that I know that you want to be notified about, I guess, notifications of the course. And also don't be shy and let me know if this was too hard or what. Okay, I know it was super fast and it was meant to be that way. It's a crash course on things that maybe you have seen before or not. I'm not sure. Okay.
I'm sorry, I don't know if this was covered in the syllabus, but the classes, the recordings are gonna be uploaded to your site or?
Yes. So this was recorded. I'm gonna post that on my website most likely. That's what I understood. But yeah. So see you next time. Yeah. Press 1-5.